Welcome to our presentation. We are going to be discussing the forces associated with the physics of flight and how they are governed by Newton's laws.
I'm Gabriel Campillo.
And I'm Susanna Nix.
All right. Today we'll be answering two main questions. What are the forces of flight and why are they important in physics and engineering? We'll also be doing an overview of drag, lift, thrust, and weight.
Let's start with a discussion of weight. Weight is the simplest of all the forces in terms of calculating, but it is the main contributor to what makes achieving flight so difficult. To take off, you must have enough lift to counteract gravity, and as planes get larger, it becomes more of an issue. We have encountered this force before. It is given by Newton's second law and governed by the mass of the object multiplied by the constant of acceleration due to gravity. As we want to take flight, one of weight's opposing forces, thrust, must be equal to or greater than the weight to attain liftoff.
Next is force. There are two main explanations for lift. One is through Bernoulli's principle and the other is through Newton's third law. Bernoulli's principle states that as speed builds up over the curved edge of the wing, wind gathers and creates a negative pressure. This low pressure creates a pulling force which pulls the plane wing up and in conjunction with the plane. As the aircraft ascends, the area under the wing serves as a vacuum of positive air pressure that has to be filled by the movement of the negative pressure. As the wind fills the area underneath the wing, it also creates an upward force. Through Bernoulli's principle, we understand the role of wing shape, and we learn that wing shape determines the body area. Newton's third law's explanation states that as wind pushes into the wing head-on, it creates an equal and opposite reaction downwards, and this allows for a plane and the wing to start driving upwards as the wind hits it. For the sake of calculations, we'll be using Newton's third law, and mathematically, that means that the lifting force is equal to the lifting coefficient times 1/2 the density of fluid times the flow velocity squared times the body area. Through our research, we discovered that air is usually measured in normal temperature and pressure, which is 20 degrees Celsius and 1 atmospheric pressure. This gives us a density of 1.2 kilograms per meter cubed. Next is drag. Drag is the opposing force to thrust, and drag is accounted for in the form of air resistance as an aircraft cuts through the air. Thrust pushes the vehicle forward and as it encounters the mass of the air it pushes through, it experiences drag. Similar to friction, drag will always oppose the motion of a mass through a liquid. However, this opposition to motion should not be confused as a reaction pair under Newton's third law. These two forces are not equal in magnitude, or else the plane would not be able to accelerate through the air. To calculate drag, we use the following equation. The drag force is equal to the drag coefficient times 1/2 the density of fluid times the flow velocity squared times the body area. And we also notice that the equation for drag and the equation for lift are the same, except for the coefficient that we use, which is either the drag coefficient or the lift coefficient.
Next up is thrust. Just like lift is needed to get the plane off the ground as well as keep it in the air, thrust is needed to get the object in motion. Thrust is also what determines the speed of the aircraft and propels it forward. Thrust is a third law reaction force produced by expelling exhaust gases at high speed in the opposite direction of the motion of the plane. It acts in opposition to drag and weight. Just like previously discussed, however, it is not a third law pair with either of these forces. Thrust is calculated very simply. As depicted in the equation, thrust is directly related to drag. Drag must be multiplied by the flow velocity to calculate the thrusting power, and thereby the force of thrust. There are several real-world applications of these forces. They are heavily analyzed in aeronautics and aerospace applications. Any aircraft you've seen, even drones and RC planes, have considered these forces to allow for flight and enjoyment in certain cases. Here are some examples of those four forces at play in real-world applications. Firstly, space exploration. We all know that rockets must generate immense thrust to overcome Earth's gravity. Engineers carefully balance the payload, like cargo and satellites, and fuel requirements for maximum efficiency. Another area where these forces are considered is in aerodynamics. Wing shapes, called airfoils, are optimized to generate the maximum lift, even at lower speeds, like during takeoff and landing. Winglets, which are vertically angled extensions on wingtips, reduce drag, improving fuel efficiency and maximizing lift. Now that we have overviewed these four forces, let's run through an example in which you'd analyze them and use their constituent equations. Say a plane weighing 213,200 kilograms with a wing surface area of 27 meters squared travels through the air. Over the course of a 1-hour flight, the plane uses 2.96 times 10 to the 7th kilojoules of energy to provide a thrusting force. Calculate the velocity of the plane. We're going to start off by making a few assumptions. First, we're going to assume the air is at normal temperature and pressure, meaning that the density is 1.2 kilograms per meters cubed. Next, we're going to assume that the wing shapes are normal, meaning that the coefficient of drag is going to be 0.05. We're going to use the particle model, and we're also going to assume a windless day, meaning that the velocity flow of air is going to equal the velocity of the plane.
Next, we have the visualize step. In this, we drew a free body diagram depicting the four forces that we've discussed. We have the force of lift, the force of thrust, we have drag, and weight. As depicted, the thrust and lift force are greater than their equivalent forces, which would be weight and drag. This to show that the plane is in motion and ascending and moving through the air. As part of the visualize step, we wrote down our knowns. We wrote down the air density is 1.2 kilograms per meters cubed, and using the table on the right, we calculated the drag coefficient to be 0.05, assuming that the airplane wing was in normal position. The area was given to us in the question, and it is 27 meters squared, and the energy used throughout the journey was 2.96 times 10 to the 10th joules. Now for solve. To begin, we defined our three equations, which is power is equal to the drag force times the flow velocity. We defined what the drag force equation is, and then we defined power as energy over time. Next, we set energy over time equal to the force of drag times the flow velocity, and through algebra, we defined that the flow velocity is equal to energy over time times velocity. With that, we set the drag force equal to its full equation, and through some more algebra, we derived that energy over time is equal to 1/2 the drag coefficient times the air density times the flow velocity cubed times the area. And through that, we derived the velocity function, and then we plugged in and got a final answer of 216.59 meters per second.
Now let's double check our answer. We calculated a final velocity of 216.5 meters per second. Converting this to a more standard unit, we found that the plane was traveling 483 miles per hour. This is on the lower end of the spectrum of typical cruising speeds, but considering the flight was only 1 hour long, it is well within the normal range. Plugging the units into our derived velocity equation, we found that the joules, which is kilograms per meter squared over second squared, divided by the time, which is seconds, times the density, which is kilograms per meters cubed, times the surface area, which is meters squared, derives down to meters cubed over seconds cubed. We take the cube root of this, which gives us meters per second, which is, of course, the standard unit of velocity.
And as for what we learned throughout this project, we discussed four main forces: lift, weight, thrust, and drag. Throughout the project, we discovered that these forces are related, but similar to gravity and the normal force, they are not reaction pairs, as in Newton's third law. We also researched and discussed many applications of the forces of flight in engineering and physics.
And of course, this project could not have been done without research, so here are all of our sources. The pictures were cited on the slides they were used on.
Thank you.
Thank you.